All right, so today we're going to be talking about chapter 15 on power. So power is an important concept in statistics. Of course, the term power is used many different ways, but we're going to talk about what we mean in the context of statistical analysis. So learning objectives, being able to define power, recognize the elements for the formula for D, which is effect size. That's something that's needed to calculate power. And then being able to describe how the alpha level, typically which is 0.05, sample size, sigma, and the difference between mu and a mu, mu sub 1 and mu sub 0, or mu naught, affects power. And then what questions do you need to ask before determining the sample size needed for a study? So we're kind of getting at a deep philosophical question here. How many volunteers do I need to recruit for my research project? Some of you may be asking this exact question in a semester or two when you're working on a capstone. So power, this is how we define it. This is the probability of correctly rejecting a false null hypothesis. Okay, that's very wordy. Probability of correctly rejecting a false null hypothesis. Okay, so if a null hypothesis is false, we want to reject it, right? And if we do reject it, then we're happy. So this is the probability of a good outcome, the probability of making a correct choice, correctly rejecting a false null hypothesis. Now remember that beta is the probability of making a type 2 error. That's failing to reject a false null hypothesis. We should have rejected it, but we failed to just because we didn't get a p-value below our alpha level. Okay, so power actually is 1 minus this probability. It's the probability of correctly rejecting a false null hypothesis. So remember, power is the probability of doing the right thing, of making a correct choice. Okay, there's a lot going on in this figure, but this is a visual depiction of power. Okay, so these are two sampling distributions of x bar under the null hypothesis and then under the alternative hypothesis. So the means, these are the mean under the null hypothesis, the mean under the alternative, and this is postulating that the alternative hypothesis is true, that this is actually the true hypothesis under the true mean under the alternative hypothesis. Okay, so you can see there's some degree of difference between here and here. Now this is the area that this is the area that we want to focus on is power. Okay. Now, if you get if you do get all these x bars and compute t statistics associated with each x bar, remember a t statistic, that's part of the formula. Some of them are going to be larger than your critical value. Okay, and critical value, that's the if you get a t statistic as or more extreme than your critical value, then you reject the null hypothesis. Okay, and it makes sense then that this area shaded here is your alpha level. Okay, so higher t statistic is associated with a lower p-value. If you get anything lower than your alpha, then you're going to reject the null hypothesis. Okay, so remember your alpha is really a probability. So this is the probability of getting a test statistic as or more extreme than the one you observed if the null hypothesis is true. So this is wherever your p-value is, you would shade in, from here over, and that's your p-value. Now, if it's smaller than your alpha, then you reject the null hypothesis. Okay. Now you can see that this this area here is power. Okay, so if a t statistic falls in here, then you reject the null hypothesis, and you are in this zone of correctly rejecting that null hypothesis. So if you're going back to like a dart throwing analogy, if you're throwing darts, if you land in here, then you are in a good place. You've correctly rejected the null hypothesis. This here you've rejected it, and this is the probability that you've rejected it correctly, okay? Because the alternative hypothesis is true. Now, remember the definition, going back here, is 1 minus beta. So you can see here's the full probability, which would total to 1. 1 minus beta equals your power. Okay? Now, the main thing to keep an eye on is you want power to be big. You want a large probability of making a correct choice, right? So if you were to shift some of these things around, shift the distributions, shift alpha, if you were to change the shape of these distributions through differences in sample size, it's going to affect the size of this area that denotes power, the probability of making a correct choice. So we're going to talk specifically about alpha level, sample size, sigma, and the difference between mu1 and mu0. Okay, now I've got a little applet here that I'm going to see if I can pull up. Oh, perfect, it worked. And this shows the same kind of thing. Let me make this a little bit. Let's see. Restore some. No, there we go. Here's the default settings. Okay. So here are two distributions. This, it's not indicated here, but this has a mu of 0. And here's the distribution under the alternative hypothesis, and this has a mu of 0.05. Okay, so it's just a little bit bigger. Now, here's alpha right here, and here is our power. Okay, so right now I'm just going to kind of play around with some numbers and see how the number here and also this area change in shape. Okay, so we first wanted to look at alpha level. What happens if I increase my alpha level? Say instead of 0.05, say it was 0.1. Now we don't often do that, but sometimes you might. And what do you think will happen to your power? So that means we're going to move this back. It's going to be a larger area. Okay, so now it's 0.1, and now you can see we have increased our power from 0.408 to 0.552. Okay, so beta and alpha are related, and if you shift around alpha, then you're going to decrease your beta, which means you're going to increase your power. Okay, so the probability is going to be higher that you're going to correctly reject a false null hypothesis. Okay, now remember, alpha represents the type 1 error, so you might not want to do that because you're going to increase the probability of rejecting a true null hypothesis. If the null hypothesis is actually true, it's more likely that you're going to reject it if you have a more liberal cutoff, an easier cutoff for your p-value. Okay, so alpha, if you increase alpha, then you're going to increase power. Okay, now how about sample size? Let's look at sample size. Well, let me get to that later, actually. Let's look at sigma. Okay, so if sigma is bigger, then things are going to be more spread out. Okay, so let's double it. Power went down significantly. Okay, so you can see that now these two distributions, their means did not change, but they are more spread out. And so there's more overlap between the two. So if you increase sigma, then you're going to decrease power. Okay? If things are more spread out, basically it's more likely due to just chance, because there's more variability, that you're going to get an extreme test statistic. Okay. Let's look at the difference between mu1 and mu2. Okay, so what if we just move these two distributions apart? So here's this one, and let's say instead of 0.05, let's say 0.15. Oh, whoops. Okay, that's not a bigger number. That's a smaller number. I meant to do a bigger number. Let's say 0.5, okay, instead of 0.05. Okay, so now our power increased. Okay, so if you have a bigger difference between the two, means, let's say we make it 1, and then your power is going to increase. Okay, and that kind of makes sense. If you have a big difference, that if the difference between the null and the alternative is truly large, then it's more likely that you're going to get an extreme test statistic and a small p-value. Okay. We can make it even bigger, okay? And now we're like almost, these are so far apart, it would be so weird to get, if we got a test statistic this extreme, it's so weird that it would actually be part of this distribution, that the null hypothesis would actually be true. Okay, okay, then the last thing, the sample size. And I saved this one for last because this is the one that you can really have any kind of actual effect on. Okay, you can actually do something about, typically. So let's say we double our sample size. What do you think is going to happen to our power? It went up significantly. Okay, let's say we increase it a whole bunch. Okay, now it increased a whole bunch as well. Okay, so if you, this is the main concept that you need to remember for power as a researcher, is that if you increase your sample size, you're going to increase power. Remember, as we increase the sample size of a sampling distribution, it gets narrower, so there's going to be less overlap between those two distributions. Okay, and that's the thing that you have the most control over as a researcher, is how many subjects you recruit. Okay. Okay, so I'm gonna go ahead and pause this one and start a new video talking about